Hello and welcome everyone. I'm Cristina. Join me to another episode of Reverse Engineering. Let me start with a short story. I had a very interesting question on the Udemy Reverse Engineering class, which led me explore the subject of API monitoring further. Thank you very much with this occasion to our students who took their time to do exercises and practice and inspired me to create this video. To make our long story short, we figured out that it's possible to bypass API monitoring tools with simple assembly tricks. Exciting, isn't it, guys? This video will focus on function interception using Rohitab API Monitor, which is really awesome. Many thanks to its authors, by the way. We will start with a classic type of sample that downloads and executes a payload. It will retrieve a binary from a URL location and execute it. The sample was crafted manually without any attempt to being stealthy. First, we have a location from where the payload will be downloaded. Then the name of the binary file. Then a call to a function defined above. In this scenario, we're using another very useful tool, FakeNet, for traffic interception. We're using it to see if the download and execute sample was successful. We'll see it in action in a second. Let's start from the code. Here's the first function. This C++ code uses functions from WinInet library and is compiled for 32-bit platforms. The logic is straightforward. We first open a network connection and we're using this custom user agent. Next, we set a timeout for the connection option. Next is the URL. If everything is successful, we create a local file. Then read in a loop all the information from the URL and save it into the local file. If it weren't for all the errors checking, the code would have been a lot shorter. Let's compile it. For some reason, FakeNet is in the process of stopping. Let's close the terminal and instead reopen it manually. Take the location of the compiled application, navigate to the folder in another terminal, and execute it. We should see the corresponding request in FakeNet. Here it is. Recognize the name from the code. Also, the default FakeNet binary was run. See the message box. Because of the logs and message prompt, we know that the application works as expected. Let's see in API Monitor what types of interceptions are available. We're only focused on internet-related APIs, so everything from this category has been selected. We're going to monitor a new process using context switch method. All of them behave the same in relation with our test application. Feel free to play with the code and with the other methods of attachment. We should have all the function names called from our program. Internet open, internet set option, internet open URL, then a lot of read operations, and finally 2 internet close handle calls. This is the usual behavior, but we're up to something more interesting in this video. Bear with me. We have another function called getHTTPStealth, which, you guessed it, it's supposed to be stealthier. Don't worry about the assembly blocks yet. They are explained later and in the follow-up video. We use a few tricks here. Right from the beginning, notice dynamic functions loading. Most important fact here is that in order to hide our function calls, we need to change the way we use resolve function names. We will use this piece of shellcode over here to manually find the address of getProcAddress function. Although it's very interesting, we will not deep dive into the shellcode now, but we'll explain it in the next video. Just keep in mind that at the end of this shellcode, we'll have in EAX register the address of getProcAddress function. This function is used to resolve other functions' addresses dynamically. Our goal is to obtain the address of getProcAddress manually at runtime. After that, we will be able to load any other function dynamically and fly under the radar of API Monitor. Remember that we obtained the location of getProcAddress at the end of the shellcode and save it in a local variable. Then, use it below to resolve all these functions dynamically. Useful trick to know. Run the payload again, first by itself, in a terminal. We printed two addresses here for verification. The second one was obtained manually via the shellcode. The first one was directly available for us to call because getProcAddress is exported by kernel32.dll library. GetProcAddress is easily intercepted by API Monitor when called the normal way, thus allowing it to trace and record even the functions loaded dynamically, not just the ones statically linked. Let's see the shellcode in action. We load the second application in API Monitor and check the difference. Make sure the FakeNet dummy applications runs correctly, then check the intercepted APIs. See here, no internet-related functions have been intercepted. Compare this output with the previous case. Huge difference. All the calls loaded using the shellcode trick are invisible to API Monitor tool. Finally, let's discuss another cool trick, also based on some assembly magic. But first, let's look at the assembly code for getProcAddress function. There's something interesting there. There are many ways to find the function's code, but we're using Immunity Debugger for now. Then, navigate to the list of inter-modular calls performed by our program. Browse through the code until we find the familiar strings and recognize our functions. Let's find all the intermodular calls. Right-click on the assembly code, choose Search for, then All intermodular calls. It should be around here. Follow it in the disassembly view by pressing Enter. Its first 2 bytes contain a move EDI instruction. This is added by the compiler to support runtime patching. These 2 bytes can be overwritten with a jump instruction to redirect execution to another place. So instead of calling getProcAddress, we could as well start executing from getProcAddress +2, skipping those 2 bytes. To do this, we need another neat assembly trick involving a couple of jumps, calls, and labels. Let's have a look what's happening in this code. In this code, we want to resolve the address of Internet Open function using getProcAddress trick. First parameter pushed on the stack is the name of the function to be resolved. Next, on the stack is a handle to the module containing the function to be resolved. The handle is obtained a few lines above. Check this out. Next, we have a call to allocation few instructions down. The trick here is that the call instruction will push the address of the next instruction on the stack. Next execution will continue from the third byte of getProc address and finally return to the address previously saved on the stack. At the end of this short block, the address of the resolve function will be placed into this local variable. We need to change a bit the code, following the previous execution. The function we resolved via the shellcode was also resolved again below. We don't need that, so comment it out. Okay guys, let's see. Almost there. Let's rebuild the solution. We have a compilation error because the file was still opened in the debugger. Let's close it and move on. Now it recompiles without problems. The application should still run okay, and we should get the fake mini message box. We actually forgot something very relevant. We need to uncomment this line over here. It will increase the address of getProc address with 2. Remember the trick, right? Again, quickly recompile and retest. It should behave exactly the same since, remember, those 2 bytes that we skipped are not relevant. Actually, I forgot to delete this hex address over here. We don't need to know that, so let me clean it. Again, it executes exactly the same. Notice here the 2 bytes difference between the printed addresses. Now, back to API Monitor to see what it can intercept in this case. Start monitoring using context switch attach method. Program crashes and there are no APIs intercepted. This is very probably because API Monitor itself hooked the beginning of the function somehow. Interesting trick, although a bit complicated to pull off. In the next video, we'll deep dive into the shellcode we used here to locate function addresses manually. Thank you very much for watching, and thanks to API Monitor authors for this very useful tool. See you in the next episode.